This conference will now be recorded.
Hey everyone, happy Friday. So we have a pretty packed agenda today. Anthony and Dennis have been kind enough to come back from Leti in France. It's 5 p.m. or something on a Friday evening, so we know they really want to do this. They're going to finish the discussion they started a few weeks ago. Young is going to do about 5 minutes in the storage workshop and an update. And then if he's online, I think he said he can join. Rohit from Google will do about 20 minutes on some proposal he has in mind. Okay, Anthony, it's all yours.
Okay, thank you. That's following the slide we showed last time about our state of the art and the different demonstrators we've done at CEA. I just want to go through those one quickly to show what are our vision and on advanced packaging. So we talk a lot about 2D, 2.5D, and 3D assembly scheme, and we believe that both 3D and 2.2 and 2.5D integration scheme are complementary in the sense that we think that 2.5D is well suitable for scaling. Actually, it allows to interconnect different chiplets at package level, and it's easier to implement, but sure, less efficient in terms of bandwidth per power. And the 3D assembly scheme, we saw it very interesting for modularity in the sense that we are stacking chips in a 3D way, give you a better performance, better efficiency due to the shorter distance and the smaller interconnect pitch as well. So we think both make sense. And the idea is to be able to scale the system at package level and also to have this modularity of playing with chiplet on top of them. We also believe it's a good approach to have towards heterogeneous integration, I would say, in the sense that we could a bit like, for example, Foveros done by Intel, having a kind of active interposer in a more mature technology, if I can say, which could be cost effective and which implements the system backbone and scalable at package level through the die-to-die link in a 2 or 2.5D manner, and having 3D chiplet on top of them, stack on those active interposer, which allows to play with different chiplet and build different system with, in this case, the chiplet that could be in the most advanced technology, and implementing almost the processing element and the nearest memory only, which allows to make smaller chiplet in the most expensive technology, and relying actually on a more mature die active interposer for the global infrastructure of the system and the backbone. So looking to those two links, if you first talk about die-to-die link, today we're more focusing on serial die-to-die interface than parallel one in the project we are developing today. That's to avoid passive silicon interposer or EMIB. Passive silicon interposer, it's a great object, but we already plan to stack two dies on together, so it will like introduce another level of stacking, which will even increase the project price. And EMIB, we see EMIB coming, the EMIB offers, or EMIB like silicon bridges offers coming also on the other side, but yet today we don't have access to the EMIB technology. So die-to-die link would enable to integrate different dies that could be available on the shelf, I would say. Even so, for sure, they need to be compatible at least from a PHY point of view, and obviously also for data layer, but the PHY is the first key element, I would say. Clearly, compared to 3D integration, it relaxes a lot the package, the constraints at package level for the implementation and the need for layout, code design, all this stuff. But one drawback of that, it's the IP availability in different technology, assuming we want to go through on heterogeneous integration on package through die-to-die link, the IP availability in different technology could be an issue. And also limiting factors because of the maximum frequency reachable in different technology. Anyway, clearly the interoperability is key for that. So yeah, we see clearly the lack of a standard on such kind of interface, and we clearly think and are convinced we need to go for a standardization of such interfaces if we want to be able to ensure the operability between different chiplets from different sources, because that's the actual real goal actually is to be able to build some system taking chiplets from different sources and different partners. On die-to-die link, yeah, we have discussed with different IP providers, and they all have different solutions. On the PHY, clearly the 56 gig or 112 gig USR SerDes respecting the CDI standards look to be the preferred solution, but we are still at around 1 or to 1.5 picojoule per bit. And clearly, yeah, we're facing the lack of standard defining the architecture details in terms of data encoding, fake usage, data packing, even pinout footprint, and so on. So there's a different approach. There's also different approach looking promising. I think, yeah, I presented that one last time. I found this paper from NVIDIA proposing a ground reference signaling concept, reducing the number of wires using switch cap and the ground as reference. Very interesting. But that was just a kind of research project. I think, yeah, I would like to be able to push that concept a bit further and see what is just available on silicon and what could be the gain on that. But just to open for another solution. Concerning the Mac, yeah, again, still there's no standard. There are different Mac proposals. I've seen people, yeah, proposing interlaken as a Mac, or even the CXL data layers, which we found quite interesting. But again, a standard is clearly required to guarantee interoperability on that. And concerning CXL, I think, okay, it's depending on use case clearly, but I think it could make sense to stay close, if not aligned, to the PCI roadmap in terms of Mac and protocol. Clearly, the PCI stack is quite heavy still, and it's not suitable for everything, but at least those developments are going in the good direction, I would say. For instance, we think that the data layer, I mean, the very lower level above the PHY is for CXL very well optimized in latency. It could be suitable for an SMP mode. I mean, just connecting two die together, the same die. And what could be interesting also, assuming we have this first data layer that is compatible with CXL, is to add the additional protocol layers when needed. That could be an adequate solution for a more high-level communication than CPU to accelerator, for instance. Even so, that one, I mean, the protocol you may add there, it's clearly heavier and not suitable for SMP, but I think we could have in the future some request to make on a package actually what people are doing today on board. I mean, typically bringing a large CPU and an accelerator chiplet together in the same package connected through a die-to-die link. And that could help actually go in that direction, I would say. For 3D links, the interoperability and standardization effort has to be done, but I think it's a bit less of an issue for 3D because we are not in the same situation in the sense that we are not going to find any 3D chiplet suitable for a given interposer on the shelf. So the footprint, the chiplet footprint itself is anyway strongly constrained by the interposer one, in particular concerning power TSV and 3D connection. So I think, yeah, clearly it makes sense to go for standardization on the interface for 3D, but it's not such an issue as it is for die-to-die, I would say. Today, our preferred strategy for 3D links would be to have a shared OpenRTL model for 3D plugs, PHY, data, and network layer. PHY could be actually very close or an optimization of an IB or a bench of wire that we could also have in die-to-die in a parallel die-to-die implementation. And yeah, the idea is to have the data and network layer to support the virtual channels so that we can come with a full NOC structure through a 3D interface. So clearly, the standardization will help anyway, but even so, it's less of an urgent issue, I would say. And just to mention, yeah.
Sorry to interrupt, but is it okay to ask a question in the middle?
Yeah, you're welcome.
Okay, I just wanted to understand what you meant by the 3D chiplet would be designed for a given interposer, and I just want to understand how the 3D and the interposer are connected.
Yeah, in here I'm talking about stacking two dies in 3D. So having a chiplet directly stacked on an interposer die. And in that case, because the full power structure and the communication is given and defined by the interposer, to stack a die on top of it, you will have to design that die for the interposer itself. That's what I mean.
So you have an interposer and then you have two dies stacked on top of it? Is that your configuration?
No, in that case, it's more an active interposer, a bit like I show here. It's an active interposer on which you stack other dies in a 3D way, and
Okay.
it means that in that case, the interposer will present the full food. I mean the left and GDS for the micro bumps or copper pillar of ball out on micro bumps ball out on the chiplet will be fully joined by the interposer itself.
Okay, understood. So
So
your
I
interposer
just
is
meant that
actually communicating between the two stacks.
yeah.
Okay.
So we think that's clearly the best way to assemble a disaggregated chip, in the sense that it's the best way to be very close to what you have in terms of communication effort and energy in a monolithic die, because every distance are shorter and so. But in that case, yeah, clearly the die itself, the chiplet you put on the interposer is designed for the interposer itself.
Thank you very much.
Yeah, just to mention that in that context of 3D assembly and advanced packaging in general, we are also working a lot on the avenue for its industrialization. I mean, assembly process, but also 3D DFT, which stay an important topic when addressing the non-good die issue. That's almost it, I would say. Clearly, yes, today we are deeply involved in the advanced packaging design. They are willing to participate to this standardization effort for both die-to-die and a 3D interconnect. On die-to-die, our strategy is to reuse and configure existing IPs to develop a communication system. So we have a lot of activities on progressing on that subject. I think a lot of people are today working on die-to-die, and clearly we need to try to concentrate the effort and go through towards the standardization. On the 3D interconnect, it looked to us a bit less urgent, as I say, but still the interoperability is critical. Even so, yeah, it's. I think the open RTL part for that could be very interesting. And yeah, the point for us, I would say it's to participate to the effort of standardization. Yeah, you are pushing, and yeah, I would like to discuss how we could be involved in that. I think that's all I have to present today. It's actually the end of the presentation we made 4 weeks ago. I don't know if you have a question.
Anybody with any questions? I actually got a couple. One is, what is your roadmap like? You think in the coming year, what are you guys going to be working on?
Yeah, today clearly our objective is to go towards such kind of assembly with systems that could be scalable at package level through a die-to-die interface and quite modular from application and use case point of view using 3D assembly scheme. So at CEA, let's say we have the architecture side architecture is on one side, and also the technology development at Leti, and we're working together towards this kind of scheme.
And do you have any work in sort of the non-interposer based space, or is all your work is on it with interposers? I'm asking, it's not a comment, it's just it's a question.
Yeah. Yeah, we have done some design with passive interposer actually already, but that's almost well established in the industry today. I will say, and since we are more a research center, we are working towards next generation, and that's our vision for next generation on advanced assembling. In addition to that, we also have some more advanced research on photonic interposer, such kind of asset as well. But we believe that this kind of scheme could make sense as a project in 3 to 5 years time frame.
So when you say photonic interposer, you mean you are doing co-packaging to bring in the photonics into the together with the ASICs?
Maybe I'll let Denny comment on that question.
Denny speaking. Yeah, photonic interposers mean that you have waveguides, for example, here in the interposer, so that you can communicate through optical network on chip through the interposer. So we've made a point-to-point communication demonstrator, and we would like for coming years to work on a multi-chiplet communication on a photonic interposer. So within this interposer, we have defined and designed an optical network on chip, and then each chiplet is able to communicate to any of the others through this optical network on chip. So the reference design is made, so the RTL is done, but the demonstrator is not still there. We will work in the coming years on these demonstrators. It's quite not an easy demonstrator because you have to mix photonics, 3D links, because you still have some 3D electrical link for configuration. So that's our target for photonic interposer.
Very interesting. Thank you very much.
So this is Ravi. I have one question. So you mentioned this 3D chiplet. What kind of chiplets you have as a top die or bottom die from an application standpoint?
We made a demonstration that we show you 4 weeks ago that we call Intact, that was presented to the ISCC in 2020, in which we made an active interposer that actually implements the complete system infrastructure plus power management and even DC-DC to power this chiplet. Sorry, there is some noise. I can't hear
Yeah,
me.
hang on. I'm going to put Ravi. Yeah, Ravi, you can go on. Someone's getting feedback. Yeah.
Yeah, so we have already done a demonstrator with, I think I may find a picture on that to present last time. Ça, c'est l'interposer. Actually, we made that chip that we call Intact. It's based on 6 chiplet stack on an active interposer. So the chiplet come with, we call me Denis, it's what, 4 core per chiplet? No, more than that. And yeah, so different chiplet in the total area, the total performance, it's 96 cores connected together in a coherent way on an active interposer. And with that, we can also build chiplet with different performances depending on the number of chiplet you put on.
So in terms of application, our target is the following in the design and architecture team is the target is a high performance compute for edge application. We believe we would like to map this kind of processor in a two-layer 3D integrated circuit with the computing part as a chiplet and the infrastructure part as an active interposer. So we call it a chassis or domain-specific interposer on which you will embed the memory interface, PCI Express link if you have an accelerator, and so on and so forth. But all what is related to compute is on top with a chiplet. So this is our target for, let's say,
in this
high
case,
performance.
you have a compute over compute or a logic over logic, right?
Yeah, we have logic over logic. What we do, in fact, in the active interposer is to we don't intend to put, let's say, to embed very high performing logic, mainly memories, for example, so that you don't have any hotspot from the interposer disturbing the chiplet. So what we have done, another possibility, what we have done with this interposer is to put within the interposer all voltage regulator, as you can see here. So this is another interesting usage, let's say, of the interposer. So
that one exists as a silicon demonstrator.
Yeah. So
and the interposer itself.
Yeah. So to summarize, our view is to use the interposer for shared input-output, for interconnect, as you can see here, between chiplets, and also for a voltage regulator.
So from a packaging standpoint, this is micro bump to copper, like TSV interconnect. Or is it copper to copper interconnect?
For this generation is microbump, but for our colleagues from Leti are working on hybrid bonding, so copper to copper, just for next generation of assembly.
Okay, and then you said you stacked memory as a chiplet on top of the logic. So this memory is like some kind of a L3 cache or like SRAM?
What I said previously is, in fact, our target for next generation is to put memory in within the interposer. And this memory in the interposer could be used either as a cache or could be used as well as a scratchpad memory.
Okay, and what will be the energy for the die-to-die link, energy per bit or picojoule per bit?
Anthony, I think it's for this one you mean for this demonstrator, this one we have here?
Yeah, yeah.
And for this one is 0.59 picojoule per bit.
So this will be very similar to what we have as a die-to-die 5 for some of the parallel interface, right? Like if you look at AIB or OpenHBI 2.
Yeah, for the communication, yes. Here, yes.
Yeah, in terms of communication scheme, yes. In terms of energy, I guess we can get a bit lower because the distance are shorter. Because it's a face-to-face assembly, directly silicon to silicon, with active phase that are just in front of each other. So the distance get very, very small.
True. Okay. So in this case, the IP you use for die-to-die communication, is it proprietary to Leti or it was used some kind of an open die-to-die file?
In that case, it was actually we made this demonstrator 4 years ago, and we developed our own plug for communicating in 3D.
Okay.
Thank you. But for next generation, we are thinking on aligning to something a bit more standard, and why not reusing or optimizing for 3D connections, the IAB or that kind of interface.
Okay. Thank you.
I had a question. You mentioned embedding the memory in the interposer. So are we talking active interposer now?
In our
Yeah.
case, yes, that one is already an active interposer, and yeah, and for the kind of scheme I showed you before, in that case, it's again an active interposer with memories, files, and communication network.
Thanks.
With the TSV technologies and to power up the stack chiplet.
Mhm.
Okay. So Anthony and Dennis, thank you. In terms of working with the ODSA, that would be great. We have like two PHYs in flight, a bunch of wires, and the OpenHPI. We're working on a link layer. One of the things where it would be nice is, if we could build, if it was possible to build chiplets that could talk to chiplets you guys built, or you could assemble chiplets or build test chips and things like that. So maybe we can have an offline conversation about that. But
Yeah,
go ahead, please.
I have a quick.
yeah.
I have a quick question. So, is there any thermal modeling tool which goes along with this? Because especially when you're doing 3D stacking of the chiplets, thermal profile calculation becomes very critical. So, are there any tools available for companies to utilize to do quick thermal profile assessments?
I know that for this project we have used some we've made some thermal simulation with a tool. I think it was the one from Motor, if I remember well.
Yeah, we had a strong collaboration with Mentor, which participate to that project, the Intact project, to also make progress on their old CAD tools. And so we work together with Mentor on that. Concerning thermal effect, but also concerning 3D assembly in general and 3D implementation, I would say.
Great. I think it might be helpful to the community here if that's one area perhaps you can come back and maybe share more on how exactly that was done. Just a thought.
Yes, that could be feasible. Perhaps not myself on Anthony, but we have some specialists in-house in our design team who have worked on this with this tool.
Yeah, we obviously have to share with Mentor what's public information.
Right, agreed. So I think, Bapi, what we can do is we can just make this as a note in one of the agenda items for future to have discussion on thermal modeling aspects for 3D stacked chiplets. And I think, let's say if there are common chiplets which are being used in 3D stack, then is there any way to leverage thermal models? Is there a way to make it easier for people to put these 3D stacked solutions together with exchanging of results and those kind of things?
Right.
I have also a question. Are you
Sure.
guys planning also to work on serial die tooling interface? Because today I think there's really a missing standardization there. We can see many actors that are actually working on the subject, but not really going in the same direction. Everyone tries to reuse a kind of data layer he has in-house and so with different PHY, and I don't see a clear path for any interoperability there. Or I don't know if that's a topic you also handle at the ODSA.
So we don't have a work stream in that. The thinking was that there's the OIF seems to have something. Quite a few people seem to have something there. We haven't had a request for us to start a work stream in that space, and put it that way.
So Bapi, this is around optical chiplet?
No, serial die to die.
Oh.
SerDes.
Yeah, because the point is, I mean, parallel die to die makes a lot of sense, in particular when looking to power. But it always comes with this drawback of being obliged to have either a silicon bridge or this passive interposer. As you can imagine, in our case, going towards such kind of assembly, it would mean adding another large passive interposer that should be larger than all the die together, or having access to the silicon bridge that comes slowly on the other side. I mean, the offer starts appearing, but I'm not sure when that will be really available
so
as a mature solution.
So a bunch of wires is intended to go after that to sort of avoid to have a reasonable performance of the parallel interface that works on laminate packaging.
Right.
Okay.
So I can share some details, but we're sort of targeting a 1 terabit per 1 terabit per second per mm of beachfront with that on a laminate substrate.
Okay, that makes sense.
Yeah.
So instead of a SerDes, we're sort of targeting a parallel interface that can work reasonably well on a laminate substrate.
Yeah, it's moderately parallel. It's not massively parallel.
Moderately parallel. That's a good way of putting it.
Okay.
I'll be happy to send you more information.
It's a good middle ground between very kind of 100 gigabit SerDes and the kind of the thousands of wires in something where an interposer bridge is required.
Yeah.
Actually, that would be an area where we're interested in collaboration. If you guys are interested in that, we're interested in building test chips. We're interested in building a library of interoperable chiplets in that space.
Yeah, that would be very interesting to us as well, I think, because today, I mean, ultra short reach SerDes are promising, but okay, it's again 56 or 112 gigahertz that you can only achieve in very advanced technology node, while in our case, we would rather having solution to be able to connect different chiplets from different technology as well. I don't think the SerDes is a good option for that. And so, we will be very interesting in the approach for a bunch of wires through a laminate. Are you taking that into such kind of constraint into account? I mean, the heterogeneously in technology and so on?
Yes, that was the original intent. It would be so. Maybe what I'll do is we'll do a follow-on meeting where we have a sort of a more open discussion on this. We'll do one offline and then try to do a larger sort of collaborative meeting like this one. But yes, that's the intent with a bunch of wires is to take packaging constraints, cost into account, and design efforts.
Yeah, because I guess in that case, the packaging, the laminate itself should be of a higher class that could be a bit more expensive as well, probably.
Right, but the theory is less than the interposer.
Yeah, sure.
Okay, wonderful.
Yeah,
so I think we got
okay.
so the bunch of wires, the thermal modeling, and I think if we had some how to build a chiplet library, these are 3 areas where we can collaborate. And we've got some work on the link layer too, which I can share with you.
Okay, yeah, thanks a lot.
Okay. Thank you, Bapi.
Thank you, Anthony.
Outstanding.
Young? Young, you still on with us?
Yeah, sorry, I'm on.
Oh.
Just
Yeah.
the audio interface on this thing is driving me nuts.
Hey, Rohit, we'll take about 7 to 10 minutes for Young, and then we can do the discussion you had in mind.
All right, thanks.
Okay, so I think basically all I wanted to say is that we will be having our the workshop on the POC hardware that we have. This is now scheduled for June 11th, just under a month. And what we're looking to do is to openly talk about the different architectures around any chips that are designed by chiplets. So the last time that I was on the call last week, I showed a few different designs intended to take advantage of the chiplet design. And the hardware is great, but the other piece that we needed to this was the design of the surrounding hardware, the server and et cetera, as well as the software, which I think is actually going to be the hardest part of all of this. So the software part, I think, is going to be the most challenging overall, because before anyone makes a chip, they're going to need to have software that works. And we have some basic designs that we've come up with, and we're essentially asking for comments so that we can continue to develop this space. And I'm trying to see if I can share my screen, but I did have some slides just to go and show what this looks like. Are there any questions for anyone while I'm trying to figure out this interface? No? Okay. Sorry, I can't find the share button on this interface. Anyone know where that is? Ah, there we go.
I think it's the share screen at the bottom, right?
Yeah.
No luck?
Sorry, just having some issues with my computer right now. I've got Windows over Windows, just won't let me
Do you want me to share the agenda?
No, I'm sorry. Okay, can you see my screen now?
Yeah.
Okay, so we have a couple of different basic models. And the models that we're talking about are, number one, an add-in device. And I just wanted to go over this again briefly for anyone who may have missed it last week. But the add-in card device essentially replaces this model on the left here. So the current model.
You may be sharing a different screen. We're looking at a textured brown background on your desktop.
Oh, I'm sorry. Let me just see if I can move that over.
But now we see it.
Okay. Okay, so on the left-hand side, okay, on the left-hand side, what you're seeing is kind of the current architecture that most people are using. There's a SmartNIC going to a host with many SSDs. On the right-hand side is a kind of a proposal, which is a network going to an ODSA device that is connected to the host CPU, but the ODSA device itself is connected to many SSDs. So this has a number of different advantages to it. Number one, of course, is the latency. Number two is the size of the host CPU that you would need. You would no longer need to have the host do all of the work. You can do it kind of right off the SSD. And an advantage to this model is that you can do something like rating directly on the ODSA device. So rather than push that up to the host, the ODSA device can do the rating across many SSDs. The second model, and I'll skip over some of this, that we have is a drive device. And in this case, the host itself is actually the exact same as what we have today. The major difference being that the ODSA chip is now placed on basically on the drive. So this drive connects through PCIe in the same way that they do today. And it pushes the computational work directly to the NAND, or very close to the NAND. The nice thing about this one is that it will scale very easily on today's servers. We don't need to have a new server designed for this sort of a model. But the downside is that because it's so close, you cannot do something like rating. That's problem number one. And problem number two is power. current U.2 form factors, for instance, allow for up to 25 watts. And our SSDs at maximum speed, and I know others are somewhat similar, can be as high as 20 to 25 watts or 23 watts. So you don't have a whole lot of power in which to use this. This means that the overall software architecture will have to be very different between the drive device and an AIC device. And part of the understanding as to which of these will be more popular for which reasons is part of the reason for the workshop, so that we can openly discuss which of these makes the most sense to do. So I just want to go through kind of briefly what we're going to cover in the workshop. Happy to take any questions if you have any.
Sorry, I had a question. If you could back up one slide, I just want to understand again where that thing sits. So yeah, there you go, that AIC device. So this box, right, that says network, or that has a box around it, that is a storage tray or storage blade. Is that what it is, or is that actually a compute node or compute tray with SSD on it, and the host CPU is the one that's doing, all the stuff?
Yeah, so in this model, in the add-in device model, what we're talking about could be either one. But in general, what you would be looking at is something that is somewhat akin to a Hadoop node, if you will. So if you're familiar with the Hadoop model, you're doing kind of large-scale scans of data. And the challenge today is that with a single, with the traditional model, you might have two CPUs here, and if you try to put more than 4 or 6 SSDs, you will likely saturate those CPUs with lock operations and a whole bunch of other work. And that doesn't allow for very good scalability.
So before you go too far, let me ask questions. The Dupe node, which I've never heard of, basically its function is to grab a bunch of data locally and then pre-process it. I'm just trying to understand the use case from the beginning. Sorry, I might take up too much time. My bad.
Normally I wouldn't stop you, but since we've got one more item, I wanted to sort of just get to the workshop and our ask for everybody so that I can leave enough time for Rohit. I apologize.
Sure, no problem.
So we want we need people the attendees' help for the workshop here, and so that's one big thing I wanted to cover today, if it's okay with you.
I'll save my questions for the workshop. I'll talk to you off.
Thanks, man. I apologize.
Okay, no problem.
You have another slide on the workshop, yeah?
No, sorry, I can't find that one right now.
Okay, hang on, then I will share my screen for a second.
Yeah.
Give me 1 second. And Ravi, if you have anything else to add, please chime in as well.
Well, so while you're bringing that up, maybe I can just say that the term I used was Hadoop, not dupe.
Okay. You want to, Ravi or Ravi Swami or Young, you want to go through this by any chance, or you want me to? What's your preference?
Yeah, if you can just go through this, yeah.
Okay. So the rough agenda we have in mind is Kevin's feet. So we roughly have there are two key components. One is centering the workshop around the idea of offloading storage acceleration, and we really have two things in mind. Three components to the workshop. One is a review of all the options we have considered as a group. The second is a panel on the particular model, which I believe, David Allen, you've signed on to moderate, if I have it right. I saw David Allen online somewhere.
No, I'm here. Sorry, I was off trying to get my mic off. Yeah, yes, Bobby.
Okay.
No issues.
And wonderful. And then we have a how do we go build the workshop where we're at least where Quinn and somebody else TBD is will build We'll sort of lay out a roadmap for how we want to develop stuff. All of this will be orchestrated by Young and Ravi Swami, who's online as well. If you have an agenda item you'd like to insert, please reach out to Young or Ravi or me. And we're aiming for 625. And we, as usual, if you think people, our general goal here is to sort of create a community of people working on this use case and developing a software infrastructure. Our goal is to build build an infrastructure that will that will help us create room for a hackathon on this in about 2 quarters. Is that fair, Young? Ravi, 1 or 2 quarters?
Yeah, that should be fine. We'll also be covering the TCO aspect on this as well, and including some of the architectures that were proposed by Young, and also the software, how we're going to model it. A couple of options that we will give, and it'll be open for discussion and inputs on that.
Yeah, I would say that some of our goals here are to get to the point where people can begin to make TCO arguments. So when somebody who is considering making a chip takes a look at the ODSA model, they can at least begin to get the basic tools to figure out, well, what is my total cost of ownership? What is my ROI going to be? These are important things for them to figure out in order to move forward with a project, and we need to get to that point.
So if you're interested in participating, if you have somebody who you think will be a good speaker, if you have some ideas you'd like to share, please ping Young or Ravi or me. And oh yeah, Sam's going to open the workshop for us, right? I knew I forgot something important. That's basically it on the workshop. All right, Rohit here has a proposal which I just looked at, which he's dreaming if he thinks he can get through it in 10 minutes. But thanks, Young. Thanks, Ravi. Rohit, it's all yours.
Yeah.
Still
So,
online.
I know that. Can you hear me?
Yeah.
All right. Okay, so I guess we have 10 minutes, so I'll jump right in. Basically, as part of the last business work group that we had as ODSA, there was a big need that was highlighted, which is how do we enable an open chiplet specification so that everybody can move this ecosystem forward. So at Google, we've been working and thinking about this quite extensively for some time, and we are happy to say that we have made some progress, and we have come up with a specification which we call the Open Chiplet Specification, which we believe can help move the ecosystem forward in this direction. And we shared that at the end user working group beginning of the week, and there was some comments that we should share it more broadly in CDX, and I thought it would be good to share it with all of you in this work group as well. So we don't have much time. That's the context behind it. Let me give you a little bit of, I'll share this document with you right now, and then maybe with Bobby.
Hey, do you want to share your screen, or do you want me to share my screen? What's your preference?
Let me see how I can share.
Okay.
Yeah.
I pulled up the document in case you need it, but
can you guys see it?
Yep.
Awesome. Great. So so the overall philosophy of this open chiplet specification. So we want to include all the components necessary to build interoperable chiplet, and put the must-have requirements as well as provide flexibility. So we have tried to model this specification around IEEE, where you have normative and informative sections. So you'll see that through the specification, and we will make it totally open. So, and we will utilize standard interfaces. So these will be all open source or industry standard. And we do want to make it a very adoptable standard. So we provide enough programmability for the vendor base to provide customization, right? So if any of the end users, data center hyperscalers want to get some specificity in the chiplets, we provide that capability for the vendors to utilize. So I'll pause here if there's any questions on the philosophy of this specification or any question about the intent behind this. Okay, so then I think
So
I'll just
wait. I've got one,
yes.
or I got a sort of a generic one. I'm wondering. So this is there's a very detailed document, difficult to absorb in 5 minutes. I'm not saying that. I think there's an introductory meeting. I've got two questions. One, should we schedule a separate full hour block for this? And two,
Yes.
okay. And two is, how do we relate this to the work that is ongoing? And is that in my mind that should also be one big thing. But those are two sort of immediate comments in my head.
Okay.
So, what I was thinking is, chiplet design exchange group has a very similar philosophical approach, at least high level. I think that 1 hour discussion can be done in the CDX work group because participants there are already probably having strong opinions, as well as they will help in linking what is in the document here with the work they are doing. So that would be my suggestion.
So DJ, there is also a lot of interesting management work, which I believe hasn't been considered yet, which I think is vital. So I think CDX plus, having a 1 hour discussion here is also a good thing on top of the 1 hour at CDX. That makes sense. Okay.
Yeah, so we can take it many ways. My intent here was not to go over all of it in detail. I just wanted to give a brief peek at this since we have limited time, and also see if we can share it in some shared doc so people can look at it and maybe comment on it or internalize it and think about it before the next meeting in the future.
You should be able to send us a link that's non-editing, right, from the share button there. So if you just put that in the chat, then we can all have it. Yeah.
Okay. So I'll do that afterwards. But let me run through this in 5 minutes so you guys have the context. So what we have done is we have stated that there are multiple ways chiplets can be used, right? Some folks talk about, hey, putting an accelerator. Some use cases have, okay, you want to go from a die to die to a high speed interface. So we are not going to specify those aspects.
Rohit, can you go to a smaller, like 90% or 75%? We see a very small portion of the doc. Thanks.
Is this better?
We have to pull all those abbreviations into our lexicon.
Sorry, say that again.
Yes,
that was a joke. We'll talk about it later.
Yeah, Ali, the answer is yes. I think we should absorb all the lexicons which are coming up into one document. So yes.
Okay. So what we have tried to do in this specification is to provide a chassis. And based on the chassis, you can build your own custom chiplets. And what this chassis contains are multiple layers. So we have a management layer, as Bapi talked about, which enables you to poll the chiplet and get information from it, discover it, and things of that nature. The other one which we have is security layer. We believe a security layer is very important to provide trust in chiplets as a possibility for next generation systems. We've also specified a build layer, and the build layer is required for any chiplet to be manufacturable. So it would have, and debuggable. So it would have concepts like JTAG, boundary scan, all of those would be part of the build layer. And then we have made an attempt to kind of give a physical physical form. So things of okay, what kind of form factor we should be able to utilize. And we want, this is a tricky one because you want enough flexibility while also providing interoperability. So we have put some thoughts there as to how this can look like. And then we have provided some more guidance in terms of what kind of requirements we would need from the chiplet provider in terms of ESD, thermals, and things of that nature. So that is the normative section. That is the requirement for any chiplet to have, so that they can play in hyperscaler data centers. Along with that, there is a whole section of informative specifications. So these are specifications which we are only providing you as guidance. By intent, we have not specified the data path. So we have not specified what kind of die-to-die you should use. You can use BO. There's a lot of standards there, right? There's BO, there's OpenHPI, there's XSR, there's many standards. So we deliberately do not specify that as a must-have, but only provide you. What's that?
I'm joking. There's only two. I'm kidding. I'm sorry.
Yeah. So we don't want to constrain the end user, like the hyperscaler or the provider, in what you need to provide here to be compliant to this standard. Similarly, on the high-speed interface, there's many ways to slice and dice the cat. So we're not specifying where you make the cut lines. You may make them at the MAC layer. You may make them at the PCS layer. You may make them in the FIFO layer. So all of those are just informative specifications. So I ran through this in 5 minutes. I don't think.
So this is fantastic. How about, unless if nobody has, DJ, if it's okay with you, tentatively let's aim for 611 for a follow-on discussion. I think this reads like a wonderful chiplet marketplace specification. Then that gives us enough time to sort of share it inside CDX and then come back to this group as well.
Yeah, I think that sounds, and I think in CDX we can have, in fact, we should spend multiple meetings to discuss this, because this is a great start. And is twofold. One is to understand this better, and the second, to understand what is going on within CDX, where some of this already might be covered in some form or shape. And that way we bridge the gap and then move this forward.
Awesome. All right. Hey, Rohit, there's also, I put a link to the doc in the minutes. I'll share this out, and then we will spend an entire hour on 611 and maybe even the following week to sort of flesh this out.
Okay, great.
Hey, everyone. Thank you all. Yeah, Bill, go ahead, please. I was going to stop recording and then begin a new recording for the next meeting. Please go ahead, sir.
So I'm just trying to say, how do we download this? This is really, as you say, awesome.
I'm going to put a link in the minutes, and I'm going to send it out to everyone, and then you should be able to access this.
Thank you.
Wonderful. Thanks all. Happy Friday. Ravi, I'm going to stop it.
This conference will now be recorded.
And the amount of logic required to drive, so if we go into an organic substrate, clearly you can't do 20 micron or 50 micron bumps. But if you drive them at 32 gigabits per second or 40 or whatever, you need maybe some DSP, or do you, if we're doing really short links? And so, I would really like to understand, is a bunch of wires interface around this die going to be 10% adder, or if we actually put down, a bunch of wires, this silicon interposer, and then there's maybe ultra short reach USR or XSR or something like that with a 32 gig transceivers or 40, and that's organically you know, does the actual logic of driving the higher speeds consume more or less compared to the pads required for the extra bumps, etc., and the extra silicon interposer costs? I think if we could build on this to get intelligence around that overhead of the edge of the die, that would be great.
Sure. Yeah. So I think some of those answers that come out of other BOW. Well, we'll just cover BOW for now. Yeah, the logic, compared to the silicon area, compared to the bump area, is considerably smaller. So the bump area dominates on a bow on organic laminate approach. Okay.
So you've got bow. So you've got bow high speed, which goes up to 16, I believe, and that's for organic, right? And then you've got the bow simpler ones that are
bow basic and bow fast. Yeah, it's same thing. The logic is considerably smaller than the bump pattern.
What about if you did a 32 gig or a 40 gig NRZ ultra short reach interface?
Yeah, I'm not sure. That would likely need to go to the IP providers, but my guess is it's still going to be smaller.
Right, and in which case, you know, this is an area that I'm interested in. In which case, it sounds like it would pay to if silicon interposers are expensive and organic interposers are both cheaper and more accessible to the industry as an industry standard, then my gut is telling me, you know, the extra logic, and we still need to be around a picojoule per bit, I guess. It's a case of, is there a trade of an extra half a picojoule per bit on this? And I think that's where some of these business discussions need to be had. And on top of this, how do we get to one single interface that we can use in the industry to start with? You know, at the moment we've got HBM, you know, and we've got transceiver I/O, and we've got a bunch of wires I/O. So if I'm a silicon designer, I've got to decide to put all three of these on and make a decision as to how many of each I put on. Whereas if I could just put one interface on and I say, well, it's you know, I really think we want.
So this was a discussion about the cost model of partitioning. So maybe we need to go back. I mean, yeah, there's some assumptions in there about that area increase. There are other things about this. Like I have an idea, you know, maybe the next step in this model would be to think about the, what do you call it? The down noding of part of it. So if you want to make the next more complicated model of, say that now you took some of the area and then moved it to a cheaper node, and how would that, you know, play in? So I don't know, what is our goal here? So I think this is a really good demonstration, and you know, and good one to put on a slide to convince people it's a good idea to do this or look at it. But our goal, right, was something more of a tool, right? So what would be the next features we would add in this tool to make it useful for someone who's, you know, you have to estimate how much larger the die becomes by down noding it, right, and things like that too. So, and then what we need to truly make this a useful tool, would we need to embed this wafer map tool into it somehow, so that, you know, when you change the size of it, you get a new yield and die per gross die and net die type of thing, right?
Yeah,
so,
yeah. Another thing specific to this, if as the die gets smaller and smaller, you're not talking 10%. You know, for a given edge area for a given I/O, your percentage of your I/Os gets bigger and bigger as the die gets smaller and smaller, as the chiplet gets smaller and smaller, right?
Yeah, he did that kind
of. So that's quite an important one, really, because he's got 10% on this chart for everything.
Well, it's 20. It's 20% when you went to 4-die. And again, I'm just using round numbers.
Fair enough. It would be good if we could get the bunch of wires ones actually in there to automatically compute the real estate of a real interface we're proposing. And compare
I mean, I think what we can do is build a model and then share it out, and you can find your own information and put it in there, right? But
yeah,
kind of, let's think about what is the next step in making this model useful to those who want to do the economic comparison, right? And then they figure out what assumptions they need to have available that they can then populate on their own, right?
Right. Yeah. There's one thing to note. Even with if we consider bow, it comes down to, what's the bandwidth you need, and then how many slices deep you go in. You could be 1 to 4 slices as it's currently written, and that affects the area. So it's not a very simple thing to say, oh, just put bow in there, because there's a lot of assumptions. So what I wanted to do is just make the team understand the economics and enable you to be able to do it yourself. Right?
Extend this lovely generic model and just bring this in. And if on the basis we're trying to get to an industry standard and we're open here, I'm assuming all of the bow ones are, everybody knows about them, and you can get access to them. So we could build this model with the bow stuff, and then if somebody wants to throw in their particular flavor of interface, they can show the merits of theirs versus others.
So Javier, and I think Ali, my recommendation is probably the next step could be we can take this model and then where it says packaging, and let's add some of those variable. And again, we have some packaging expert in this call, and from OSATs and even from across the industry. How does everyone think adding packaging as another variable for the overall?
I think packaging and test. So let's pull on both those experts. I think that is the next priority. Good idea. I think that's a perfect.
And that could be built on the Excel model, which Javier is showing, because the online tool does not call out for packaging and test, but we can build into this Excel model, and then iterate.
I might suggest also maybe putting together a short user's guide, or maybe one of these tabs. Just write some text about step-by-step how to use this model, the link to maybe a public guide calculator that you can use to calculate some of the values that need to go into the spreadsheet, right?
So what I would suggest we can do collectively is use this Excel sheet as a starting point to eventually make it into a decision model, which is we have all the right variables captured, and then individual companies can benefit by programming their own options, and the model spits out the right path for those options selected. So, let's say if I am a company building an ASIC and I put my parameters in, and then it gives me a suggestion of what is the best path forward, what kind of chiplet sizes I should go forward. I think if this business work stream delivers that model, which is usable by everybody, that's a great value add.
Right. Yeah, I think I want to make one comment before I need to drop off, but the increased packaging cost, if you're in 2.1D to go into multiple die is insignificant, right? It's just assuming you're still in the same package area. And the data die doesn't increase the layer count, which these larger devices tend to have a higher layer count already. So that's a key thing. But the additional cost in going to 2.5D is going to be dwarfed by the savings you have in silicon cost. Okay, so just want to make that point. The additional cost of going to 2.5D is not going to be $40 to $70. Right?
True. I think we just need to.
That's clear.
Javier, yeah, I think I'm with you on that. I think it's just that we need to somehow find a way to model that. So if you can do me a favor, or just respond to the distribution and share this Excel file if you can, and so that. And now probably let's discuss how do we add some of those packaging costs, whether 2.5D or 2.1D, and it will increase slightly, but I agree with you. Silicon saving is much more overwhelming than the increase in packaging cost.
Okay, I'll add some annotations to this, and then so that way people understand, because some of these values need to be entered in from the output of the spreadsheet. I'm sorry, of the web tool. But I'll put the link of the web tool and I'll let people know what to insert where. Okay.
That's why I said maybe a little user's guide, like so as we build this, we keep it updated so that someone can step in, understand how to use it, and then take it in their own direction or add to it. It's like almost like a open source, right, type of thing that we're putting together. So you'll probably want to take snapshots so make sure nobody messes it up.
Yeah, I think what we can do is we don't need a separate user's guide, Ali, but the suggestion is well taken. We can make Excel sheets so well annotated with every cell clearly described. I've seen, people must have seen financial models in Excel where you can calculate home mortgage, whatever it may be, right? So we can create a model like that, which becomes self-explanatory.
Sorry, guys, I'll need to drop off.
Thanks,
Yeah,
Javier.
Please share it
I'll
with us.
take the first crack at that. Okay.
Thank you so much.
Right.
All right. So I think that was a good discussion. Ali, do you want to share your taxonomy for the different ODSA nomenclature?
Yeah, so I was wondering if anybody had the link to what Rohit was sharing at the last meeting.
I think I will be able to dig it up.
If you could share that, because then I was going to start grabbing some of his terms, though. Those are I mean those aren't really very industry standard, so I don't know that we that would be more of a situation where we're trying to establish something, right? Okay, anyway, so let me get started. Is this big enough? Should I zoom in? Or what do you guys think?
If you can just increase the document size, the full screen, so that way, yeah, because we see two documents, one on the left.
Well, okay. Okay. Well, I just wanted not to show too little of the screen here. Okay. So, we wanted to have a cartoon to help illustrate this. And so I don't know who it was actually who put in a bunch of cartoons here. So I think this is where we'll center our discussion around, 2D, 2.1D, 2.5D. And then maybe from this, we can also lead into some of the other terms that we use, in terms of the assembly. Because I think it's natural when you're looking at this diagram, then we can define some of the assembly stuff. Let's see, I think I'm going to review that we're going to get rid of this chiplet accelerator module. That's not a term that we'll use, so I'm going to remove it from the document. Going once, going twice. All right, sold. Okay, so, and then we're going to piggyback on some JDEC terminology. Did anybody check if module was in JDEC? Then we can use the word chiplet to describe one of these, like a chiplet module or a chiplet multi-chip module, which is a little weird, but we can use the word chiplet to modify them. And then the definition of a chiplet is really about a chip that's really designed to work with other chips inside, some kind of package. So if it could be packaged alone, like it has the drive strength, for example, or to be packaged alone, then we wouldn't consider a chiplet, right? Okay, I'm going to assume silence is agreement.
So Ali, I think this is the same definition which we discussed in the past, like the chiplet one. And
right. I'm just reviewing what we did before. Now I want to get on to the new stuff.
Okay.
We talked about a die-to-die interface. Okay, so that may or may not be optimized for in-package operation. We are going to maybe you were going to do some kind of diagram to help define these A to B interfaces, right? So that's still to be done. Okay. All right. So let's talk about package types and the silicon within them. So we've got a conventional flip chip package. And then when we go to 2.1D, now we're talking about, a die chiplet on top of that conventional 2D flip chip. And then 2.5D would be where you add in like an HBM or, so basically 2.5D brings in another layer of silicon. So here you can see there's an embedded bridge or with the memory, but you're still using the, I guess, organic interposer. Is that the idea? So who added this section?
my question is that when you talk about 2.5D, you can either do it, talk about this as being a MCM. Then the other way that you talk about substrates, you also mentioned silicon bridge.
Right. So
that's
the thing is that they are two different things. So it's a little mixing it. You know, this kind of 2 to 3D definition, right, is pretty fuzzy. You know, if you have an active interposer, are you suddenly 3D? You know, or do you need to go is something more than that is actual 3D, right?
And you're also in between this substrate, organic substrate approach. So I'm thinking about organic substrate without bridge, organic substrate with bridge. Then you have fan out, then you have 2.5D. How does that sound?
So, wouldn't bridge be 2.5D then?
I'm just thinking about the hierarchy. The hierarchy would start with MCM on conventional build-up substrate, MCM with conventional build-up substrate plus bridge, and then we have fan out on top of substrate. Then we have 2.5D. I'm thinking about this being a grouping depends upon complexity.
And then you said 2.5D, and what does that equal? That's
2.5D would be silicon interposer.
Yeah, interposer or RDL interconnect. That's kind of how I look at it.
And
would
so
bridge also be part of this? Because the bridge is really a silicon interposer replacement. It's just a smaller piece of silicon that encompasses the signals that are connecting the two die.
And then how does HBM play in here, right? Because that's already basically a stacked die. I mean, in some ways it's 3D, but nobody gives, if you have HBM, and it doesn't seem like, at least in this definition, we're giving it credit for being 3D. So, you know, I don't know if we need to worry about that, or just consider HBM to be like a die, right? HBM stack is like a chiplet.
Well, today that I know of, where you have basic and HBM, they are typically on silicon interposers, and in development, they are doing on fan out. I am not aware of HBM on high density substrates. Oh yes, I think I have seen discussion on HBM on substrate with bridge, but I do not know whether it is commercially available or not.
So I think, Bill, the HBM with silicon with EMIB integration is only from Intel. If you see, Intel has offered a whole bunch of product where they are integrating HBM using an organic substrate with silicon bridge or EMIB, what they call. But I have a question for this figure. Can you go back, Ali? So in this one, can you enlarge the figure? I just want to see why it is called 3D.
Which one?
Yeah, this figure. It says 3D including other element. I'm just trying to understand why this is 3D.
I think it's because there's a chiplet stack here, right? That's what makes it 3D. Like an HBM is considered to be the same as a chiplet in terms of dimension, right? You're not, by doing HBM, it's not actually going to 3D, but now here you have some other stuff. But if the interposer, even the embedded interposer is active, then are we at 3D?
So the one on the top which says 2.5D with embedded bridge, I think that's called in the industry 2.5D, and the one in the bottom where there is a chiplet stack, I think that is 3D if there is a chiplet stack. I know it says chiplet stack, but I don't know if there is more detail here.
Right. It's general. I mean, is it useful for us to try to define these? I mean, to put in our lexicon, or maybe we don't worry about this and define things a little bit more at a lower level, like we were talking about base die versus active interposer. What's an RDL? What's a bridge? What's the difference between different links? Different. All these terms are we're working at a lot of different layers of abstraction, right? From physical to protocols and stuff, right? So kind of having some definition for all of them would probably help people to move between the different layers of abstraction, right? This is way too complicated, I think, for this. But does it help us? Do you have an opinion, DJ? Does it help us to define what the stages are from 2D to 3D?
Yeah, I think so. And in fact, I was looking at this as you were explaining, and obviously I'm not a packaging expert at all, and I was hoping to understand the difference between, let's say, 2D and 2.5D. So I was using myself as guinea pig to see, hey, can I understand this nomenclature? And honestly, these drawings are not very clear. So for instance, the 2.5D with interposer and HBM memory drawing looks so much similar to the 2D drawing, which is right above that, a little bit above that, except for HBM being replaced by die and chiplet. So it's very confusing in some sense for me, for instance, why is something called 2.1D and why is something called 2.5D?
I can explain, Dharmesh. So mostly people call 2.1D in the industry when they are using organic interposer, which is a non-TSV and more like a RDL interposer, and 2.5D typically people call when they are using silicon interposer. So that's probably the one key difference.
So if you look at this picture, it's got a silicon interposer connecting the HBM and the chiplet. So that's where the half a dimension comes in. And then this one's also got some silicon, right? So that's half a dimension.
So the 2.1D or the 2.3D typically uses the high density interconnect of the PCB to do the connection. So it's been used before MCM style. I think even AMD probably used it for one of their EPIC generations, but it uses high density interconnect of the laminate to do that. Versus when you get to 2.5D, you're actually using either silicon or RDL. So you're moving from the PCB to the package and silicon. That's how I understand it. I don't know. It's confusing.
Yeah. So so let's step back, right? All of us, let's step back. The reason why we are creating this ODSA lexicon is very simple. The entire community will keep having new set of individuals joining ODSA over period of time because the momentum is growing. And at the same time, there are more people like me who do not understand a lot of these things. So I would love to read this document and get at the same level of understanding as everybody here, right? And right in this call, we kind of clearly see that reading this document and we are still not at the same level of understanding. It should not require any expert hand-holding beyond reading the document, because the document should be self-evident and explanatory. Otherwise, it doesn't serve the purpose. So one suggestion I have is, usually, if we create stack up using, let's say, simple Excel sheet where each cell can be colored, and then we can, have, stack up built 2.1. This is how it looks like, 2.2, 2.5, and we can copy those back in here. But that makes it very clear to identify each layer. Like, people are talking about that little orange layer in the middle between dye and the green layer. Now, it's very difficult to look at it in the figure, but in Excel sheet, we can even mark that cell with some name, and then I can compare, okay, here, that particular sheet layer is missing here. So I think we want to make this very simple. And again, the idea is not for us to come up with some universal definition which industry agrees on. The idea is we create a simple nomenclature for ODSA community. And in fact, we can also choose in this lexicon to remove any nomenclature which is so confusing that it's beyond the scope of the lexicon. We can remove that also. For instance, somebody comes up and says, oh, there are 1,000 different ways to define 2.5D. I don't agree with this. Then we just remove it, right? We say, okay, we cannot come up with a simple explanation. This document initially is only for commonly used terms in all these conference calls, and we are all on the same page when somebody is presenting and talking about these common terms. And I go refer to this document instead of asking anybody, and I understand what anybody of you is talking. So I think that would be one way to make this simple. And I'm happy to help on the Excel drawings if needed. But of course, I don't have the domain knowledge, but I'm happy to contribute because I'm giving suggestion. That means I also have responsibility to contribute to the solution, and I'm happy to do that.
I'm going to call out Anu, who is asking me if she could put some drawings in here. So would you mind, kind of starting from these drawings, and let's do these same 2D flip chip. That's a just conventional, then a 2.1D, 2.5D, and kind of a 3D, and just some diagrams with enough labeling that we can really understand, and then a short description and based on these, but based on your understanding. Would that be okay?
Yeah, that's fine. So, DJ, you want me to do that in a spreadsheet?
You and I can work on it offline together. So let's do that. You and I work offline, and then you can present whatever we create. Happy to work with you. And I think we need.
You guys have this shared, right? So you should be able to have.
Yeah. So me and Anu we'll figure out a way to work on it. And I think.
Okay, great.
Ali, why don't you quickly go through the rest of the document to see where we need to keep contributing? This is, by the way, awesome. Sure. I think people will really use this over a period of time for self-education. So that's part of the exercise. And then we should jump into the problem statements in the business community, which I think Ravi had started polling. So we should leave the last 15 minutes of the call because that's also a very important topic for us to discuss. Thank you.
What I like maybe is for these terms to be defined within your process of putting together those diagrams as best you can. Maybe we won't be able to do all the different bonding because that would require a lot of different diagrams, but maybe we could do a small diagram that just shows the difference between bumps and hybrid bonding. Let's see, then over here we have an RDL2 just so everything is defined, right? So someone coming in can pick it up. Then we've got the stuff that's really about interfaces. And I wonder if someone would take a stab, maybe I could volunteer Alan to take a stab at kind of putting down just a general definition of what is a PHY, what is a link layer, what is a protocol, so that when we're looking at, how do we make DAI talk to each other, we can all understand what that means. I'm a guinea pig here because I don't, all this interface stuff is new to me. So it'll be nice to have that. So can I have a volunteer? Can I put your name, Alan? No, Alan. Anybody else? No interface experts?
Sorry, Ali. Alan here. I just stepped away for a minute. What are you looking for?
I'm just looking for someone to write down a short definition of each of these terms and any others that you think would be relevant to the interfaces.
Okay. I'm not an expert in the silicon layer, but I can have a go.
And you can lean on the group from the link there team to help, right? So this is, you're just kind of helping to pursue right people, because we do need to divide and conquer this document. Ali has done a great start, but we all need to figure out where we take ownership of a small section and just devote, a little bit of time to clean it up, and then over a period of time, it will all come together.
Ravi, I have a suggestion. Sorry, I interrupted somebody else. Sorry. Go ahead.
I've been happy to work with Anu on the definition of the 2.5D, 3D, and etc.
Great, thanks, Bill.
Ravi, I had a suggestion along those lines. Basically, fan out MCM is broken into two pieces, right, or two categories: chip first, chip last, and then 2.5D is the silicon interposer, or the TSI. And that's a suggestion to look at, the definition between 2D, 2.5D, and a 3D configuration. Maybe we should put in the chip first and chip last also.
So, Swami, that's more from a process standpoint, but ultimately from a packaging definition standpoint, would that change the packaging definition from 2.5D versus 2.1D, how you are attaching the die?
Yes, it does, because you put, the die on interposer then on the substrate versus, just the RDL. If you look at TSMC's definition, the info versus the CoWoS, it maybe, maybe on a higher level, you're right, absolutely. Maybe the differentiation is not made there, but
Again,
I don't know.
Swami,
It was just a thought process.
No, I'm all up for that, but question is how deep we want to make this document, and I think what you are referring is chip first, chip last. In my understanding, those are more process driven, like even like front end, back end of the line, like all of these, which is written here. Again, we can include, it's just that somebody needs to take ownership to add those content, and those are good. Again, I am aware of it, but maybe not everybody is aware of it in in the community. So is it something you can help with, Swami?
Oh, definitely. And to just what Bill was mentioning now, I think it could be covered as a part of 2D, 2.5D, 3D.
I think we give it its own section. Leave the structure as one, and then the assembly process kind of part as another. Just because we need to draw a line somewhere anyway, you could keep going, but I think this kind of fits a little bit more. That's for people talking high level about what is the general complexity of it. I mean, then how you're going to put it together is the next level of complexity. So I think it's a good separation point. So, and it goes together with these other terms as Ravi was saying. So if you wouldn't mind, and add anything else that you think would be useful, and then we'll discuss it at a future meeting. I would say, if you're unsure, throw it in here, and then we can always call it back in our discussion. If it turns out to be redundant or just maybe too much complexity or too much depth, then or we wouldn't want to get that specific. Is that okay, Swami?
Yeah, sure. I will send it to Anu then. The chip first, chip last definition.
Sure. I'll share this link again. So anyone with the link can edit, right?
Ali, can I have last 10 minutes to discuss the problem statement voting? And I know is that okay?
I think we've assigned out plenty of work. Thank you.
Right, and this is a work in progress. So Ali will keep working on this document over every call. So let's move to the problem.
Okay, cool.
Thank you.
Okay. Thanks, Ali. So let me share my screen, especially, okay, let's see if you can see my screen. You guys can see my screen?
Yeah.
Okay. So the way I see is, I think, so we had an action item last time, 2 weeks ago, that everybody will update this column D, and as well as people will vote, especially those who have not voted. So I think I want to close the voting now because otherwise we will be keep dragging this. So can we just agree on and see which one is getting the most vote, and then just narrow down and then drill down those as a problem statement moving forward? Would that be okay in last 10 minutes of this meeting?
Sounds good.
Okay, so I'm just looking at the color. So this row is getting the most vote for number 1. And I can show what this row is. And is anyone on the call does not have the link? Tell me.
Ravi, why don't you just post it in the chat so that way every time, everybody immediately can get access to it. That's it.
Okay, I just pasted here again. So
perfect. Thank you.
Right. So going back, so this is the one which says cost model for chiplet that works for multiple chiplet. And I think Anu, you added this. So again, I don't want to get into the content at least for today, but let's say if everybody is okay making this as a number 1 problem statement for us to work on. And I know Javier in the beginning of this meeting shared a wonderful model from a chiplet standpoint, and we need to just build that model, include packaging and some of the testing and some of the other elements.
Sounds great. I agree.
Yeah, I agree as well. So
okay.
Ravi, in fact, while you're running through this, I'm going to capture in the same spreadsheet the action item and next steps, and that way at least something is captured.
Okay, so Anu, you're okay with this?
Oh yeah, no, I'm the one who wants it real badly.
Yeah,
So.
that's her suggestion, her question, Ravi.
I'm very happy that everyone signed on to help me with it.
Okay. Sorry, DJ, you were saying something?
Yeah, I said that question came from Anu, so she better be okay with it.
Yeah, but then it comes with some responsibility, and that I would need her help along with everybody to have more meaningful discussion in the subsequent meeting. But let's talk about the mechanics later. But let's look at what else we have the most vote and then how. So I think this is overwhelmingly number 1. I want to pick at least 3 problem statement, and so this is one. This one, though it got most of the 3s, but also got a lot of vote. And this one right here got a lot of 2s. So between this row, and if people are wondering what this row means, I can increase the magnification so that it will not be an eye chart, which anyway it is. So this one was more around manufacturing, metrology, and this one is around define known good die and security for chiplet. And I see that details are standards for known good die across organization. How do we end up tracking the device, supply chain, whatever that is. Okay. Okay. So I'm looking for everyone's input between this, which is lots of number 2, and this is lots of number 3, and then this one, which is ties to number 14, which is this. Okay, and any input from a voting standpoint, row 15 I think has a higher vote of 2s. Yeah. Any disagreement if we make this as a number 2 problem statement for the work group?
Yeah, I think it's okay.
So, Ravi, just so that I'm capturing it properly, standards for known good die. So, are we hoping to have a quick, short document published, or can anybody elaborate a little bit, maybe a minute, on what exactly are we going to achieve here? What's the goal?
So, Anu, looks like everybody is listening to you because these two are from you. Do you want to add your 2 cents?
Yeah, no. So the only reason my name shows up on these two is because Ravi, you picked me first that day to go through what people's, major issues were, and
Oh, okay.
I just happened to be the first one. So essentially, I think the key is when you get known good die from third party. How do you really know they're known good die? Are there any standards? Is it is it our prerogative to actually set standards for chiplet vendors? Or is that not acceptable? Because I've heard that too, saying, why should somebody else tell me how to select my known good die? What is it that known good die entails in terms of the scan chains or a scan wrapper around the block that they need to give you patterns for, the chiplet vendor needs to give you patterns for? The other piece was the security protocol, which I think got mentioned somewhere else also, in terms of when you do your own chips, you tend to inject it with some kind of security protocol at some point to make sure that the part that you're putting on the field is really what your own part, right? And there isn't, nothing's been done to it or modified or swapped at some point. How do you ensure that chiplet from a vendor has a security protocol that is acceptable to you, or is there a standard across the industry that can be used? So those are the kind of things, Vijay. Right now, since most markets are vertical integration, it's really within an organization's purview to figure out what known good die is. And you know where the fault lies. If all the chiplets are coming from your organization, you have no one else to blame but yourself when there's a problem. But what do you do when it comes from third party?
So that's awesome. I think the way I captured it, and Ravi, you can move to column B because I'm trying to parse what she said, Anu said, into something very simple and specific. So if you move to column V, if you go to the right-hand side of your screen, column V, Victor. So one thing we can do collectively, I think you'll have to refresh your screen, maybe, I don't know, because it's not showing up what I've entered. So one thing I entered was, the concept of known good die, how do companies know that it's a known good die? I think that concept probably already exists today in a proprietary, monolithic, vertically integrated organizations. So one thought, I captured was, how about we just try to capture what is existing today by talking to the right organizations and have that as a first step. It's not our proclaimed standard, but we just go and find what is already there instead of reinventing from scratch. We just figure out how companies go about defining a known good die standard, and that's all we capture in ODSA and publish it somewhere.
Okay, so I have one suggestion, Dharmesh. So, Swami, do we still have you online?
Yes.
So, Swami, is it something Regan from Advantest can take a lead here? Because I know he also came to the workshop and he gave a wonderful presentation around, known good die yield from a test standpoint. Do you think is it something he can help in leading this activity?
I can definitely ask him.
Because I think it will be very nice if we can get some kind of a test house to own this, and of course all of us will work with that. And what DJ was saying earlier, that it can also start reflecting what we already have today. How people are doing it, and then so that's like current state, and then what is the ideal state, and how do we even first what the ideal state look like, and can we even agree on the ideal state?
Yeah, and we don't need to think about ideal state yet, Ravi. My suggestion is current state is working, right? Because chiplet-based products do exist in market. There is healthy, revenues generated by them, companies like AMD and others. So all we do is we start with something which we know is working. It may not be absolutely perfect for every situation, but we don't even know right now what is working. So first 6 months, 8 months, all we do is capture working with Fab House. Hey, these are the things which we have as a standard for known good die, and then we communicate that within ODSA. So business work group does the job of bringing the knowledge from very bespoke area into the open community, and that could be the simple first step.
Okay, so Swami, let's see if you can help in having a discussion, and if you want, maybe you and I can have a joint discussion with Regan and see if he or somebody in his company can help in leading this.
Oh, definitely, Ravi. Let's touch base sometime this afternoon and
Sure.
I'll reach out to him right away. Yeah.
Okay, sounds good.
Other thing I added based on the second comment by Anu, I think on the security protocol, I believe what she's referring to is more on the supply chain security. So rather than security in the operational manner, which is what I think we can work through what Google presented this morning, where there's a security block embedded in the chiplet. But I think this particular security protocol, which I believe Anu was referring to, is more related to the supply chain. And I think that kind of fits in with the known good die as well, because known good die and making sure it is known includes security aspect of it, like it's known versus unknown in terms of the origin of the die. So I think that's how I interpret what you just said, Anu, rather than a particular security protocol.
Yeah, I agree.
Could I just ask that maybe here it seems like both of these are already done for chips. It would be interesting to understand exactly what new needs to be done for chiplets versus chips.
Actually, both are already done for chiplets also, I would reckon, because chiplets are existing, right? So that's why we are going even one step further. Forget about chips. This is already done for chiplets. Let's just find out what has been done for chiplets.
But Dharmesh, all the things which is being done for chiplet is in a vertically integrated supply chain. So which means one company is pretty much taking care of everything.
That's fine. That's fine. We start with what is known, and then we say these things apply, these things don't apply.
Okay, sounds good.
So what I think suggestion is keep, we are all working on 20 different things. Everybody has a day job. So we work with the simplest problem statements and then slowly move up instead of making it so complicated that people get disheartened that I don't have time to work on it and they just walk away from it. Rather than that, we keep things so simple that people say, yeah, I can almost get you that information. I can almost get you that. And then we change it a little bit. And in a year, we will make a big progress.
Sounds good. So I want to be respectful of everyone's time. We are top of the hour, and